Okay, good morning. We're just about done here with section 10.2. 10.2 day 3. A couple days ago we talked about basic exponential growth and decay functions in these forms here. Thursday it would be, we talked about compounded interest where n is the number of times compounded per year. T is typically in years. And today what we're going to talk about is the natural base, what's called E. Well, what is E? Well, we're going to find out what E is here really quick. And probably they call it easy E. Well, before n represented the number of times compounded per year. Let's examine what happens as interest compounds more frequently like we did the day before. So to do this, we're going to imagine Helen finds a different bank that offers 100% interest. Oh, what a joy. We're going to complete this astronomical table below here. If Helen were to basically invest $1 and we're going to let it sit in the bank for a whole year, and we are going to see what's going to happen to her interest as the number of times compounding increases. So as you look at this very large table, we're taking n from 1 to 2 to 4 to 12. So we're going once, semi-annually, quarterly, monthly, weekly, and then we hit 365 for daily. And what's happening is we're just changing n in here. Well, interest compounded 100%. We're going from 2, 225, 244, 261, 269, 271. And then from daily, we're going to get into hourly and minutes and every second as time goes by. Did you realize there's 31,536,000 seconds in a year? Bottom line, what we're identifying is as n is pretty much increasing without bound, what's happening is this whole value right here is kind of dialing in on 2.72 approximately if I round it to dollars. Now this is an irrational number that keeps going on there. And the observation we're going to see about the frequency and compounding, what's happening? Well, as n gets very large, as it seems to increase, but as n gets super, super big, what's happening is our amount quits growing. Well, what's happening is our amount is impeding, encroaching on a number called E. Well, we know about pi, 3.14159. It's an irrational number. The decimals never repeat. They go on and on and on, kind of like me right now. But what happens over here in this interest formula, as n approaches infinity, t is still 1 here, as n approaches infinity, what happens is this whole quantity approaches this number, 2.71828818, blah, 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 blah. And that number in math is said to be called E. And we use it for things that are called continuous growth, things that never stop growing. They just continually grow. And it's referred to as the natural base, and we'll talk about natural logs and common logs in the next chapter as well. Well, we got to the pi. I discussed that pi. Bottom line here, here's some stuff you really don't care about, I'm sure, the guy that invented E. But basically, as our interest compounds, as n, the number of times compounding, as that approaches infinity, okay? So as we are looking in there, as n seconds, and then I could go to half seconds, whatever, n's getting bigger and bigger and bigger, it's going to infinity. This number is encroaching on this number E, okay? So when we move on to our next page here, what we're going to do is the constant E represents continuous growth. You know when you're using this continuous growth function because they actually say continuous growth. Many other mathematical properties that makes it unique, and you will see E is used a lot in calculus when we hit integration and derivatives and such. Following graphs are sketched here. So we have 5 graphs in this plane. If I had to match these graphs, Well, only one of these numbers is a decay function. 3 over 5 is less than 1, so that's got to be this one. And then I have a b value of 2, 3, 10, and 1.3. Well, the one that's 1.3 grows the slowest. The one that's 2 is the next fastest growing. That's the blue one. Red one would be 3 to the x, and the biggest b value would be the steepest curve there. So consider the function y equals m. Use your knowledge to approximate the value of e to sketch its graph. Explain your reasoning. Well, it's really not too difficult to figure out. If e is 2.71828, which will approximate e to be 2.72, because 2.72 falls between 2 and 3, the graph of e should fall right between the graph of 2 to the x and 3 to the x. It's actually going to be closer to 3 to the x because this number right here is closer to 3 than it is 2. If I looked, here's the blue one's my 2 to the x, the red one is going to be my 3 to the x, and the black one is e to the x, so that's e is 2.72, and it's getting pretty close to that 3, so it falls between those two. Shocker, huh? How do I get back? I gotta go back, okay? So as we keep moving along, we're gonna find values of f of 2 and g of 2 and estimate m of 2. We're not going to do any estimating with MathSense because I know right now at home online you're not going to do any approximation. You're just going to type it into your calculator. Well, f of 2 is 2 to the second power is 4. G of 2 is 3 squared, which is 9. M of 2 is actually 2.718 or 2.72 raised to the second power, 7.38. And it's continuous growth is what that means, okay? So it's going to bring us back to a formula you probably remember possibly from Algebra 1. I don't believe it looked like this. You looked at it as y equals p e to the rt. We called it PERT. Well, that was continuous growth. And the further along we go in math, we're going to kind of just change the numbers or the variables in it. Continuous growth is y or n of t equals n sub 0 e raised to the rt power. Where n sub 0, that's my zero term, that's my initial amount of my initial population. R is my rate of growth as a decimal. T is time, could be defined in years, days, and hours, but typically T is in time. And N of T is the population after T years. Well, why do you suppose E is used as the base here? Well, because we're talking about populations, and populations grow continuously. They don't just grow at convenient little times like in January, February. They continuously grow at a constant rate, formative rate. And then we're going to look how can we use this formula, because E is a number greater. It's a number greater than 1. Therefore, you would think it would always be a growth exponential function, but it doesn't have to be. Okay, we can use this to represent a decline in population or a decay function if we let R be a negative in value. So if our R value, if our rate of growth is negative, what happens is that curve will left to right, it will actually fall. And last page here, we're just going to bomb out, excuse me, a quick example. Population of Fredericksburg, Virginia. Really, Fredericksburg, blah, blah, blah. It was approximately 19,360 in the year 2000, and it's been growing at a rate of 2.9% a year. Well, use the formula for population growth. Well, population growth is right here. It's continuously compounding, okay, to write a growth model of Fredericksburg, okay? Well, because population always grows continuously, well, if we looked here, our initial population is 19,360. E to the R, our rate was 2.9%, which is 0.029 times T T is years. Okay? And what happens when we use that? And please remember, whenever you're doing a model of anything, you have to have a variable left in your equation. That's why I say you have to have t left in your equation here for a model. Okay? Well, let's use the model to predict what the population was going to be in 2013. Well, if t equals 0 is the year 2000, well, to get to the year 2013, if 0 is 2000, if I add 13 to that, well, t is 13 would represent the year 2013. So I just plug in a 13 and let my fingers do the walking through the calculator, and we would find out the population is approximately, in the year 2013, 28,225 people. Now, please remember we're talking about people. Please round to the nearest person. Okay. What value does your function model give for the population of Fredericksburg in the year 1980? Well, t equals 0 is the year 2000. Well, if I'm going backwards to 1980, well, then I'd have to take away 20, so t would have to equal negative 20. Well, if I did that, what's going to happen? If I took 19,360 times e raised to the 0.029 times negative 20, well, we're going to get down. It's going to actually back the population up to what it was in 1980, 10,839 or 10,840, just kind of depending on how you rounded. A couple different schools of thought there. Either one would be acceptable. And here, use a graphing calculator to estimate the number of years it would take Fredericksburg to grow to 40,000 people. Well, because we don't want to change our scale so big, we're going to let our initial condition here, our n sub 0, be 19.36. And basically, that just means our equation is given to us in thousands. So whatever our answer spews out, we would take times 1,000. So if we did this, when is my equation here equal to 40, rather than doing 40,000 and 19,360, we just made our function in terms of thousands. And basically what I did is I graphed my function right here, which is 19.36 e to the 0.029 times x. When is it actually equal to 40? Graph them both. Find the point of intersection, 25.0231 comma 40. Well, that means a little over 25 years, we're going to be at 40,000 is the interpretation of that. So basically, when I look here, so approximately when t is 25 years, it would be a little bit more than 25 years. But if I needed to know the actual year it would be, I would take that 25, add it to the year 2000. It would put me sometime during or in the year of 2025. Then we just have one more check for understanding here. And notice my interest is not continuously compounding. It is compounded monthly, so n would be 12. And I come back to my 5,000 times 1 plus rate as a decimal divided by n raised to the n times t. And if you invested $5,000 at 2% compounded monthly, never put another dime in there, you would end up having $5,636.92 in your account. There's really not a lot of thought we have to do here. It's just a little bit of application. Plug and chug is what a lot of this interest is. And that concludes our 10.3 video. Have a good day. Tomorrow's a work day.